Okay, so this is the next question that we have on the menu today, and is asking us, or it's presenting us a situation where we have a skydiver that is trying to figure out her speed. Um, and the skydiver is carrying a tone generator, pretty much just a speaker that makes a single frequency of sound. The skydiver's friend, who's on the ground, has equipment for receiving the sound waves, and the skydiver is falling at terminal speed, which means that the skydiver is at a constant velocity. Terminal speed means you cannot be accelerated any farther. That means the gravitational force is counteracted by the air resistance force that is pushing you upwards, or the air friction force. So your velocity is constant, which is pretty important for this, constant velocity. Her tone generator has a steady tone of 1480 hertz, and the speed of sound is going to be constant, and it's 343 meters per second. And it's also the same at all altitudes. That's not the case in real life, but that is an assumption that we need to maintain for this question. If the friend on the ground receives waves of frequency 3260 hertz, we need to figure out the skydiver speed of descent. So this is the first part of the question, and the second part of the question is we're trying to figure out the reflected frequencies, but we'll get to that when we get there. Okay, so drawing out the situation, we have a person, a skydiver, like this, and they have a sound maker. And we have a person down here who observes it, and they observe it at a higher frequency. So here the F source is going to be 1480 hertz. The F ground is measured at 3260 hertz. The velocity of sound is going to be equal to 343 meters per second. And we are looking for the velocity of diver, because these are the only things that we really need for this situation. Okay, so to do this, the concept of interest here is the Doppler effect. Which pretty much means approaching things increase frequency what's the opposite of approaching? Leaving things or departing things. Have decreased frequency. Okay, so since we're approaching, clearly we're going to have a higher frequency. And the equation to model this is, let me pull up my reference right here, is that when we have, right now we have a source moving towards a stationary listener. So this is the equation that we want to use. So we have F ground, so that's the observer, is equal to F source multiplied by the velocity of sound over the velocity of sound minus the velocity of source. Okay, this is the equation that we want to use. a source moving towards a stationary listener. Yeah. Yeah, exactly. Okay, so here we want to isolate V source. So to do that, we shall bring it to the other side by multiplying both sides by it. So we have V sound minus V source. And we divide both sides by F ground. So that will be F source over F ground times V sound. And we can isolate V source by switching the sides. So we can do V source is equal to V sound minus F source over F ground, the velocity of sound. And we can factor this out to make this a little bit easier to calculate. Is equal to V sound 1 minus F source over F ground. Okay, so now we can just sub in the numbers that we need and we can calculate the velocity of the source, which is the diver in this case. So the velocity of sound is 343 meters per second multiplied by 1 over the source, which is going to be 1480 hertz divided by 3260 hertz. Okay, ideally we should get something that is lower than the speed of sound itself, because we did not mention anything about sonic booms. So let's run this calculation ASAP fast. 1 minus 1480 over 3260 times 343. And my calculation for this is 187 meters per second. And that's to 3 significant figures, which is what we're given in the question here. Okay, cool. So did we get the same answer on the given here? Likely just a rounding error, but we got pretty much the same answer, so that's gotta be good. It's probably just a rounding situation. That's peculiar, but okay. Okay, so that's the part 1 of the question. Part 2 of the question is asking us if the skydiver were also carrying sound receiving equipment enough to detect the waves reflected from the ground, what would be the received frequency of the diver itself? Okay, so this is one of those situations where the ground is going to become the source now, and the listener is going to be the receiver, or the listener is going to be the diver itself. So we're going to have a listener approaching a stationary source. So that's going to be listener approaching stationary source. So this will be part 2. So the equation that we want to start off with, and we're going to do our stuff with, listener moving towards stationary source. So listener, let's just call that FD for diver, is equal to the F of the source plus the V SOS for sound plus the velocity of diver, all divided by the velocity of speed of sound. Okay, so this is listener towards stationary source because we're going towards the ground and the ground is the source. Okay, fairly reasonable. So we are trying to find the frequency as observed from the diver, and well, we actually don't need to do any algebra for that, and we have our V source, which is our diver, as this calculation. So this is actually fairly straightforward. we'll just have our V source, which is what is bouncing off the ground, and it hits the ground at 3260. So that's going to be here. That's going to be our V source. Our speed of sound, 343 meters per second, plus the velocity of the diver, 187 meters per second. So that's Ft. All divided by speed of sound, 343 meters per second. Okay, let's ask our calculator what this will give us. I expect a number larger than 3260 because, well, when things are approaching, they have higher frequencies. So that's what we'd expect here. So 343 plus 187 times 3260. And my result for this calculation is 5,037 hertz. And we want to convert to 3 significant figures because that's all that we were given in the question. So 5.04 kilohertz. Ft. Frequency as observed from the diver for the reflected wave. So the Doppler effect, this is how the Doppler effect works in action and how you can see it work. It's pretty cool stuff. Doppler effect is very useful in many different areas, not just for sound, but also in light. And we use the Doppler effect and its interaction with light to do a lot of precise calculations about how, about like space observations. Very cool stuff. Okay, is there anything else in this question we need to address? This appears to just be the a repeated part of a question, but otherwise things are good. And came to very similar calculations. Really, it's just going to be like rounding errors, so these will both be acceptable as right. But yeah, okay, cool. So solution is good. Some concerns about rounding, but otherwise answer is good. Cool.